All right, the question and answer session.
How are the problems?
That's a question.
Ivan?
I like any problem where I can just do some Euclidean algorithm.
Good.
It's a stress relief for me.
Okay, good. Let's see. Should I pull up the problems and see what I don't remember what I assigned anymore. Some of them were meant to be easier. Okay, so exercise 1 we did together. Exercise 2 we basically did together. Exercise 3 we don't have to go over. I mean, either the central limit theorem type arguments or not. Exercise 4, did you check that this number is a primitive root?
You can share your screen if it helps. I don't know, or maybe everybody's got them in front of them.
Oh, should I share my screen? Actually, I went back to the website and pulled up my lecture notes to know what it was that I said and wrote.
Yeah, maybe share the screen. That'd be easier.
Okay.
Have people refer back and forth.
Okay, so anyway, the first couple exercises were either trivial or not for now. This, check that it's a primitive root, plot and see these pictures. Okay, so you can see these pictures for yourself. Right, did anyone compute okay, I guess that's what Ivan, you were saying, you can compute the continued fraction expansion, meaning Euclidean algorithm, run on these two numbers. That's why I said Euclid could do these things. He was the one that invented the algorithm. In a sense, the Pythagoreans, I mean, he understood things about the algorithm that the Pythagoreans didn't. But anyway, exercise. Okay, did you guys find another number other than d equals 6, which has no numerator, so that when you put that numerator over 6, over the denominator, whatever the denominator is, you won't find anything that uses fewer than digits fewer than 5.
I wrote a Python script and it came back and said 54.
54, good. Was 54 just the one that you found, or sorry, Gary?
We like Ray in our group wrote a program and it was just 54 and 150 and there was no bigger number than that till 10,000 or something.
Yep.
Yeah, I only checked up to 100.
Those are the 3 that are known for a equals 4. Did you try it for a equals 3 or a equals 2? So a equals 1, by the way, we should have said perhaps. I mean, what Zaremba said is just take a equals 1. What do you get for the fractions when a equals 1? I should have made this an exercise.
The Fibonacci or something?
Exactly. Quotients of consecutive Fibonacci. So the nth Fibonacci on top, n plus first Fibonacci on bottom. So that will have all ones, and of course that ratio converges to 1 over the golden mean. Again, it's 1 over because there's a leading 0 here that's sort of implied. Right, so you can always get Fibonacci numbers, but Fibonacci numbers are exponentially sparse, right? They grow exponentially, so the number of them up to x is log x. So if you, instead of taking a equals 5 or 4 or 3, if you take a equals 2, so a equals 1, you get the Fibonacci's, a equals 2, the conjecture, there's a conjecture of Hensley, is that, again, there will be a finite list of numbers that are missing, a giant, much bigger list now, but after that finite amount, every single number will appear. So in the case when a equals 4, there were 3 numbers missing, 6 and the other 2 that you guys found. And if you set a equals 2, there will, again, conjecturally be finitely many numbers missing. After that, everybody's there. But even if you make a equals 100, we still do not know that every single number will occur. Question, okay, in the chat. The first few for a equals 3 look like this. Is there any general pattern in these numbers? So in the numbers that are missing, is that what you mean, Gary?
No, not like that. Like I mean, can we get a pattern or formula by which we can get the next numbers? Like for Fibonacci, we have the like formula kind of thing. For a equal to 3 or others, do we have?
Yeah, so well, the formula should be that conjecturally that every number, once a equals 5 or higher, that every number will occur. But what do you mean about getting, how do you want to get the next number? So this is why I introduced this semi-group, so that the next number can be obtained by taking some previous ones and applying some element. But that's sort of too greedy an algorithm. It'll get you too far ahead. Like the next number, you know, when you go from 4017 to 4018, it might be that you get 4018, but not by something that adds on to the matrix that gave you 4017, but by drastically changing what's going on there. So in fact, that's exactly the structure. This mixing of these words is exactly the structure that's that the circle method is trying to capture in order to produce lots of values of these maps, this 1-1 map or the trace map and so on. Does that answer your question? So it's very hard. That's the hard thing about these patterns. They're not patterns that are described by some nice algebraic formulation. Did you want to say something?
No, that's it. Thank you.
Mhm.
It's, yeah.
Okay. Any other questions until we continue down? I hope I gave you more interesting stuff than this. Let's see. Exercise 9. Gosh. Okay, that's trivial. Did you guys try? Did you find any more numbers here? Find something other than 1 plus square root of 5 that uses only 1s and 2s. Was anyone able to do that? That's an auxiliary exercise. I should have put that in here so that you see just how seemingly unlikely this conjecture is. Should I add that to the list of exercises? It's too late now, of course. Do you understand what it is? So I gave you one value that's in Q adjoint root 5 that only uses 1s, not even 1s and 2s. If you use 1s and 2s, find another. Find something other than the golden mean that's going to be in Q adjoint root 5 using 1s and 2s.
So is the difficulty here making sure that it's in Q adjoint root 5?
Exactly.
Not just like, because I can just like say some random like infinite string of 1s and 2s.
Absolutely. Yeah. You say a random string of 1s and 2s, and you will get typically a pretty large discriminant already with a pretty small set of numbers. Because these numbers, the traces are going to start blowing up exponentially in length. So for the square free part of that trace, or trace squared minus 4, whatever, where was it? We had this discussion over here. Well, the traces will be growing exponentially as you add more and more words. And so, yeah, to land on a square times 5 is pretty lucky. But it's supposed to happen, you know, exponentially often among these 5 to the L possible values.
You wanted it to be like fully periodic, right?
Can you? Yeah.
Yes, exactly periodic with it, not eventually periodic.
Because then you can just add in some string at the, okay.
Yeah, if it's eventually periodic, then it's still in the same field. So just
Right.
kill the leading stuff until you get to the periodic part.
Gotcha.
Yeah, so here's an exercise. So using only 1s, we know what we can find. There should have been another exercise. Using 1s and 2s, find something else in Q adjoint root 5. And I think if I recall, you have to go to length like 10 or something. You're not going to do this by hand.
Do those have any sort of like algebraic interest in that field or something?
Yes, they are. So this is what I didn't have any time to discuss, but these will give quadratic forms, binary quadratic forms with very low minima relative to the value. So this is like the Markov. These actually would be in a lot of cases, Markov geodesics. So we talked for a second about Markov last time. I can't
I'm
remember.
thinking
But
about building the geodesic over the endpoint.
yeah, exactly. So you take this quadratic irrational
Mhm.
and you look at it on the real line and its Galois conjugate.
Yeah.
And you connect those by a geodesic in the upper half plane, and you fold those mod SL2Z, and that will give you a closed geodesic on the modular surface,
Right. And you're
which
saying
also
that
corresponds to a binary quadratic form.
the maximum height is really low or something?
Exactly. And the maximum height is if it's below 3/2, then you're one of the Markov geodesics. If the imaginary part goes no higher than 3/2
Cool.
after this folding.
Cool.
Yeah, so that was lectures 1 and 2 of there's a sequence of lecture notes that I think Cliff posted in the on the website. So those go through the stuff that I was deciding whether or not I can go into, geodesic flow on the modular surface, on the upper half plane, binary quadratic forms, Duke's theorem, all those things. I decided in the interest of time to skip them and skip this ELMV problem. But you can read about them there. But it's about having these low-lying closed geodesics on the modular surface, which is actually where McMullen came to this problem from. And one could reformulate what he was saying in this very sort of down-to-earth way. So that's what I ended up presenting. How about exercise 10? Did you guys prove this?
Yeah, our group worked on it, and I think it's a direct induction argument on L.
Yep.
So,
Yeah,
like,
could be a direct induction argument, could be just look at what the process is when you add another digit. What you do to the number is the same thing as what you do to this thing.
Yeah.
So yeah, a pretty easy induction argument. Did anybody have trouble with it or want to talk about it? Okay, well, if you don't want to, don't want to ask me, then you can ask Akash. He's got it. In Akash's group. How about this one? Were people able to solve this one? Oh, good. I got one that actually challenged you. Oh no, Flavio, you got it?
I think that you just write the quadratic equation and the discriminant, and you find that the discriminant should be a square multiplied by t.
Yes.
Because the alpha is in q, sorry, in q root of d.
Yes. So one way to see it is that this alpha will be, if we think about the fractional linear transformation of gamma on, on the upper half plane, or it could have determined +or -1, so it's really just on the complex numbers, restricted to the real line. So what does it do to alpha? You'll see that by the very nature of alpha will be a fixed point of gamma. And so if you solve for what it means for alpha to be a fixed point as a fractional linear transformation. Did we talk about fractional linear maps? Does everybody know what I mean by that?
Mobius transformation, you mean?
Say it again, sorry.
Mobius transformation.
Mobius, yeah. So if you have a matrix ABCD, then ABCD acting on alpha is A alpha plus B, that's the linear, over C alpha plus D. So it's two linear maps and a fractional linear map. It's the projective action on the projective line. Right, so if you look at it from that point of view, then all you need to do is solve gamma alpha equals alpha, because by its very construction, it will satisfy that recurrence. And when you do that, you see that what are the fixed points of gamma? It has to do with the fixed points, what field the fixed points lie in. When you take a square root, the square root that you're taking of is of trace squared minus 4. Good. Did anyone try exercise 12?
Yes.
And?
I have a question.
Please.
I mean, we were thinking about, A is not fixed, so A could be equal to 1.
Okay, except for A equals 1. Yes, you're
okay.
absolutely right. A needs to be at least 2.
Okay.
If A is 1, then you don't have a Zariski dense group. If A is 1, then you have a semigroup generated by a single matrix, and all the powers of that matrix will not fill out all of SL2. So it's not Zariski dense.
Okay.
Yeah, but as soon as a equals 2, yeah, so I should have said a is at least 2.
We're not meant to assume we have 0, 1, 1, 0.
0,
I
1, 1,
guess you're not
0.
meant to. Yeah,
Oh,
I guess you're not meant
I
to.
mean that a is positive. It's a positive integer.
Sure, yeah,
So
of course.
a is like 1 and 2. As long as you have 1 and 2, then you're already onto mod q. Thanks, Ray, for that. So did anyone get it? Anyone see how to do it? Again, I told you it's pretty hard if you don't think of this trick. Should I tell you the trick?
Yes, please.
Can I get some time? Possible.
It's a bit annoying because I think we can do it if a equals 0 is in the group. But
You
Wait.
don't need a equals, you don't, it turns out you don't need a equals 0 in the group.
is it hard to generate the a equals 0 from the other elements? Modulo something, of course.
Yeah, well, so a equals 0 doesn't help you because we're going to take the intersection with SL2. So we'll take even words in these generators.
Oh.
Is it easier if Q is prime?
Not really. It's about the same whether or not Q is prime. Once you make one little observation, one sneaky observation. Should I tell you? So here's the sneaky observation. Let's say we just have 1s and 2s. If we have 1s and 2s and we look at even words in the generators so that we're in SL2 instead of GL2, on the level of the semigroup, it's very difficult to see what's going on. But if you, instead of taking only the semigroup, allow yourself inverses, then you will very quickly see that if you take the group generated by gamma A and you have 1s and 2s, that gives you all of SL2Z. So you can write the generator, your favorite generators of SL2Z in terms of some words using 1s and 2s of these matrices and their inverses. So now with that hint, how do you do this?
Sorry, did you repeat that hint again?
Yes, the hint is gamma A as this, the Archimedean gamma A is a semigroup. So I'm only allowed to take these matrices, but not their inverses. Their inverses don't correspond to the structure of the underlying problem. But if I were allowed to take inverses, my claim is that you would very easily be able to write the generators of SL2Z as words in these matrices and their inverses. In other words, the even length words, including inverses of this gamma A, if you took the group generated by this, you would get all of SL2Z.
Shouldn't be A bigger than Q? Because I was thinking to this, but
you're right for your spidey sense to go off that something could go wrong for small q. In this case, what I said is an Archimedean fact, so it actually is independent of q.
okay.
So here's how you finish it. This is the crazy thing. Once you know
take
that
like powers.
Yeah, sorry, go ahead.
That's curious. Like if you want to generate inverses, the rest is like a finite group. So if you take powers, you do get your inverse.
That's it.
And I was a bit worried about order calculations though, but I guess that's enough.
So you get elements of a group. When you reduce mod q, whatever your matrix was, you'll get an element of z mod qz when you take these generators. But this is a group of finite order. And so when you take large enough powers of that element, you'll wind up on the identity. Which means if you take one less power, you'll wind up on the inverse. So in finite groups, there's no such thing as a semigroup. If you have a semigroup, you pick up the inverses for free. So it's as if you just allowed yourselves the inverses to begin with. You'll get the same group. So because if you allowed yourself the inverses to begin with, you'll get all of SL2Z, then this will just be all of SL2Z mod Q. So that's the trick here, is to go back to the original group, allow yourself the inverses, and make Ray's observation that you'll pick up the inverses in a finite group by Fermat's little theorem.
So in the image, there'll be a word in the generators.
There'll be an image
A
in the
positive.
word, in the positive,
Yeah.
in the positive word in the generators, in the semigroup, that will be the corresponding projection that you were looking for.
That's a great trick.
Yeah, so if you didn't see that, I think without using that fact, it's pretty hard to figure out a way to, how do you make sense of this thing mod Q? It's going to be different for every Q, like it's going to be a god awful mess. And then you see this one little trick and it's just falls right out. So I had in mind tomorrow to tell you a little bit about, you see, the circle method. I wanted to say more about the proofs of these things, in particular, the proof of this main theorem from today and the one from yesterday. And the proofs will decompose into, we'll talk tomorrow sort of generally about the circle method and particular about some aspects. I'm not sure, we'll see what happens about which aspects we really go into. But I had in mind tomorrow to do the minor arcs, which will be more exponential sums, and the major arcs, which is finally when we'll see expanders playing a key role, we'll do on Friday. And it'll be sort of maybe the most advanced parts with some spectral theory of automorphic forms at a very sort of introductory level and things like this. At some point, we have to use the expanders, and that's where they come in. So that's what I had in mind. If that, unless you guys want to hear something else, I mean, it's not what I want to say, it's what you want to hear. That's, to me, the most important. Okay, some of you are happy with it. If you're not, tell Cliff, I hate this stuff, I wanted to do something else, and then Cliff will get it.
Anonymous survey, yes.
Right.
You all have an anonymous survey in your emails. All right.
Any more questions? Are these problem sets too easy? Should I make them harder? Do you have enough to do?
I felt like I had plenty to do.
Yeah, great.
All right.
I was just wondering, would it be possible to release the problem set sooner so that like we get some more time to work on them? And
see, I make them up on the fly. So because I'm not really sure what I'll end up talking about. I could try to, I'll try for tomorrow to give you some, see if I do that, then I have to fix what I'm talking about. And if you guys have questions and we end up going on some tangent that's far from what I had in mind, then I like to go on those tangents, but then it means the exercises might not be the appropriate ones. But I'll think about it. I'll try to make sure we have at least some, at least a couple of exercises. I'll prepare an exercise. There's a good exercise that I think will be worth doing that I'll prepare for you for tomorrow.
thank you. Thanks.
Sure. Lewis, oh, I see. Okay, sure. I'll stay on when we're done. You can ask the question.
All right. Well, I will stop recording now.